lightning. It's technically just a little bit smaller and a little bit quieter than the outdoor lightning you might see later today, but you're a lot closer to it, or most likely a lot closer to it than you would be to outdoor lightning, so it still appears pretty loud and pretty bright. But as I said, this is the same exact type of lightning. It's the same thing that's generating it, which is electricity that's moving through the air. And electricity is made up of two types of charges. Those charges are positive and negative. And these positive and negative charges are in almost everything that's around us. And a positive charge and a negative charge are attracted to each other. So that if you separate a positive charge from a negative charge in the air, they will travel back towards each other. Now, inside the thundercloud, there are a lot of charges. There's also a lot of things in there that can help to separate those charges, all moving around, like liquid water, solid water, ice, dirt, and dust, and smoke, and all of these things that are rubbing around against each other that causes large amounts of positive charges to separate from large amounts of negative charges. And when they eventually travel back through the air towards each other, that's when we get our thunder and lightning. Now, we are obviously not inside of a giant thundercloud here, but there are a lot of charges. And to separate these charges, we're going to use a machine. And it's not just any machine. This is the world's largest Van de Graaff generator. It's these two columns with the two domes on top standing 3 stories tall. And not only is this the world's largest Van de Graaff generator, but it's also one of the oldest, because it was built by Dr. Robert Van de Graaff himself back in 1931. So here is a picture of Dr. Van de Graaff. Oh, sorry, I apologize, that screen's not working today, so we can see over here. So that's an earlier, slightly smaller, slightly earlier version of the Van de Graaff with Dr. Van de Graaff there. Our domes were also originally separated with a tube between them because he was not actually interested in studying lightning or electricity. But he needed large amounts of electricity in order to control his experiments, which as a particle physicist was about taking particles and smashing them together, going through that tunnel there. Now, because he wasn't studying lightning or electricity, or even whether he was, he didn't in this case want bolts of lightning coming off of his machine into his laboratory. But we do want bolts of lightning to come off of our machine. So the machine itself runs the same way to separate charges, but we do things a little bit differently so that we can get the lightning. So I'm going to give you an inside look as to how our machine works. So if you can check out our video screen here, this is a live video feed. It is live video, so just nothing is moving yet. And it's underneath this right-hand column over here. So underneath here, there's like a whole basement area. And what you're looking at in this video are 3 white rubber belts. Those rubber belts are about 4 feet wide, and they run all the way underneath the column, up through the column, up into the dome. Now those belts, when they get turned on, they go about 40, 50 miles per hour. They act as a conveyor belt to convey charges from down below to up above in the domes. So the whole machine is plugged into the wall, and it uses the electricity from there, and has both positive and negative charges, where negative charges go up the conveyor belt, while positive charges stay down here in the ground. So then we've got lots of negative charges up there, lots of positive charges down here, and they're attracted to each other, but there's a whole lot of air between them. It turns out that air is a very good insulator, meaning electricity does not travel well through it. One of the reasons why the machine is so big and so tall is to be surrounded by more air. It's an air-insulated Van de Graaff generator. But as I said, we want these sparks. So what we've done is we've added different types of targets, like this one, that are the air will change over from an insulator and act like a conductor. And that's when we get the positive and negative charges traveling through the air towards each other to make our spark. Now what I'm going to do is turn the machine on. I'm not going to make the loud sparks yet, but I want you to listen and watch as our machine gets started. So right now all you're hearing are the motors that are turning the belts there. So the white belts are going about 40-50 miles per hour. In just a moment, I'll add the negative charges, and they'll take a ride up to the dome. And when there's enough positive and negative charges separated from each other, the air will change over from an insulator, act like a conductor, we'll get a spark. So now, I'm going to cover up my ears and put all of this together. And what better thing to do in a lightning laboratory than experiments with lightning? Very carefully controlled, safe experiments with lightning. So one of the most important things to understand with lightning does have to do with lightning safety. So my first question to you is, where is the safest place to be during a thunderstorm? You know, storms rolling in the summer. Where's the safest place to be? Where do they often say? My phone app tells me like every hour during the summer to do what? Where does it tell you to go?
Indoors.
Anywhere? Anywhere? It doesn't go inside, basically. It says get indoors is what I use. I haven't used the Weather Channel app lately. I've been using the Weather Bug app. I don't know, I like it better lately. And that one comes up, if there's a lightning strike within 10 miles, it says get indoors. Because indoors is the safest place to be. But keep in mind, this is the summer. A lot of times we're not near and indoors. We're out on a trip, we're out at a park, or a lake or somewhere. There might not be any buildings around. The next safest place to be if there are no buildings around is where? A car. Car, also a safe place to be during a thunderstorm. But why? A house makes sense. Why would a car be a safe place during a thunderstorm? Do you guys have any ideas?
Rubber.
Why? Rubber what?
Tires.
Rubber tires. Okay, well, your car does have rubber tires, 4 of them usually. And what's so great about rubber? Rubber's a good what?
Insulator.
Insulator, yeah, rubber is a good insulator, absolutely. Well, let's just see if rubber tires can insulate against a lightning strike. So I happen to have a rubber tire here, and I happen to have a machine that makes lightning. So let's see what happens if you strike a rubber tire with a lightning bolt. Now we would expect the rubber tire to be a good insulator. Rubber's a good insulator, so we expect that the lightning is not able to travel well through it. So keep an eye on our rubber tire up there. I'm going to cover up my ears, and we will strike our tire with some lightning and see what happens. So did our rubber tire act like a good insulator?
No.
Yeah.
No. No.
Okay, let's make sure we're all on the same page here. We've got a 50-50 going here. Did you all see the lightning strike the top of the tire?
Yes.
Yes. Did you see the lightning come out the bottom of the tire?
Yes.
Yes. Did you see the lightning travel around the outside of the tire? No. So it did travel around the outside, and it went in one side and out the other side. It traveled through the tire, which means it acted like a
Conductor.
conductor. It acted just like a conductor, in one side, out the other side. Didn't act like an insulator, but I thought rubber is normally a good insulator. But what else is also normally a good insulator? When you get enough charges, it acts like a conductor, and it's all around us? Air. And we just had our bolts of lightning travel through, what do you think, maybe like 5 or 6 feet of air? In an actual thunderstorm, a bolt of lightning can travel several miles through air. Are 2 inches of rubber going to be able to stop it? No. It's going to act like a conductor. It will not insulate your car. But many of us have heard a car is a safe place in a thunderstorm, so perhaps there's something else that's protecting us and not the rubber tires. I mean, any other ideas what might be safe about our car?
The battery.
It's made of metal. I pretend I heard that. I thought I heard someone's mumbling something. I think I'm going to say that it's made of metal. And it is. Most cars are made of metal, or at least they have a metal frame. But metal already is a good conductor. But the whole rubber tire insulator thing didn't work out, so perhaps it might have something to do with the fact that it is a metal conductor. So I don't have a metal car here, which would be really cool, but I don't. But I have the next best thing, which is a giant metal birdcage. So this metal birdcage is going to act as a model for the metal frame of a car. So here I am, basically inside of my metal car, driving. I'll be driving about 20 feet off the ground, as one does during a thunderstorm. And I am surrounded by a metal frame. Beneath me, around me, and above me. It's not solid, it's a frame, so I can get my hand out, but just like the metal frame of a car, often might be filled in with plastic or fiberglass. So I've got my model of a car here, and I'm going up to be nice and tall so that I'm the closest, shortest distance that the charges have to travel through the air. So we'll go up nice and high. I will put on my lovely stylish headphones. And we'll see what happens when a metal cage, like a car, gets struck by lightning. Okay. Still some suspense. Put this on. Pretend like I'm driving my car. Thunderstorm picks up. Drive along. Not high enough. A little closer. And magnets. Love playing with magnets. Magnets can be used to create electricity. Most power stations have giant magnets generating most of our electricity. And on the other side of the same coin, electricity can be used to generate magnetic fields. Every time the electricity strikes the cage, because it's made of a conductor all around me, tiny magnetic fields are generated all the way around the outside of the cage, keeping all of the charges on the outside of the cage. It forms a protective skin called the skin effect. So all the charges on the outside, I can even touch the inside of the cage because all of the charges stayed on the outside. As long as I didn't put my hands through and I stayed on the inside. And that is in fact why you are safe inside of your car during a thunderstorm. It has to do with the fact that it is made of a conductive material. Now, as if we haven't had enough fun already, we're going to play a game. And involves sound, as if we haven't been making enough sounds already either. So this sound, I'm going to make not with the big Van de Graaff generator here, or even a small Van de Graaff generator, but another piece of equipment called a Tesla coil. Now these Tesla coils make not just one spark at a time, but can release hundreds of sparks in a split second of time. And these two machines over here, I think they look like trees. They're about 8 feet tall with like the copper trunk and the silver donuts on top. And these Tesla coils can change the amount of sparks that come out of it at a time. The more sparks that come out at a time, the higher the pitch sounding the note. The less sparks, the lower the pitch. We use a computer to control how many sparks come out at a time. You get different pitches or notes. Put the notes together and you get a song. So what we're going to do now is play a game called Name That Tune. We're all going to play a bunch of geeky fan favorites and see if you can name that tune. I suggest you cover your ears because it does get quite loud and you'll still be able to hear it.
Yeah, Star Wars.
Maybe the Imperial March, yes, more accurate than Star Wars even. The Imperial March, yes. But I think they should use that in episode 9 when, the Imperials come back there. Okay, so that's my first. Let's try this next one. Same composer, different era. Fingers crossed. I'm sure whatever comes out, it'll sound cool. But we'll see what this next one does. If you have any questions or comments, I'll be around afterwards. But right now, if you want to sit back, relax if you can. Consider you're going to be in the middle of a giant indoor lightning storm here. We're going to have the Van de Graaff have a little bit of percussion as well. And let's fingers crossed that we get another finale song coming